All right, we'll get started. Okay, let's start. So, are there any questions? Any questions about assignment 1? A few of you have been asking me privately, but if you have any questions, it's a good place to ask them, or in the discussion group. The discussion group is very silent. I've only answered one question there. It's a good place to ask questions if you haven't. And now's a good time to ask them rather than later. Right? It's due, next Friday, I guess. Who's today? So today we'll cover the last thing that you need for that assignment, namely we'll cover branch and bound. You have a question?
Yeah, about the third question about
Okay.
form heuristics.
Let me bring it up, actually. I can do that. More informed heuristics. Yeah.
And it says you can assume the costs are positive everywhere.
Yes?
And that's all we're allowed to assume? Like, we're not allowed to assume that they're bounded by a non-negative constant? Basically, like, so we can't use the admissibility based on it.
No, you can use the admissibility. It says they're admissible, and the definition of admissible is that the costs are bounded below by a constant. Yeah. You can use that if you need to.
Well, but no, the heuristic, the admissibility of the heuristic is different than the admissibility based on.
Right, but if you're talking about, what are you asking about?
So just from, if you read this really literally, you can't use the admissibility of A star because all it says is that the costs are positive everywhere. So this doesn't prohibit the case where you have the arc length forming a geometric series.
Correct. Yeah, you can assume that the costs are bounded below by a constant, positive constant, and therefore A star is admissible for this question. Yeah, good question. Good point. Admissible heuristic doesn't imply A star's heuristic is admissible. It requires that bounded below by a positive constant for the costs. Any other questions? Okay. Okay, so we've got a fair bit to cover today. One really important algorithm that in practice is used a lot, and one of the parts of this lecture is to point out which of these many, many different possible algorithms are actually used in the real world, in practice, so we'll emphasize that. And branch and bound is one of them. Branch and bound is actually a huge collection of algorithms. How many of you have heard of branch and bound or studied it somewhere else in a class? Okay, very few. Okay, that's interesting. So we're going to just deal with a very particular version of branch and bound, which is depth first branch and bound, but it's not the only kind for optimization. But first, as usual, I'm going to recap what we did before very quickly. Distinguish between the state space graph and the state space tree. They're identical if you have no loops or if you have no shared structure. So last time I talked about strict trees versus trees, right? I mean, you probably think of a tree as a strict tree where every node has only one parent and so on. What's sometimes also called a tree is a directed acyclic graph. In other words, it's a graph with no cycles, but a node may have more than one parent. And so for both DAGs, directed acyclic graphs, and full graphs with cycles, the search tree will look very different from the search graph in general. And we looked at nodes in the search tree correspond to paths in the search graph and so on and so forth. We looked at multiple path pruning. We looked at how you would do that. If you want to find the optimal path first, it may be that you find a non-optimal route to n first and then you find a shorter route, in which case you'd have to do some surgery on the paths with the longer route, like put the shorter sub prefix at the front of them and get rid of the other one. Or, better, prove that your algorithm always finds the optimal path first, right? And this is a subtle point that We did this before, but test your memory, get your cards out, and tell me which of these algorithms, least cost first search or A star, expands, when it expands a path P ending in node N, that's the lowest cost path from a start node to N, if all the costs are positive. Okay? Yeah, it's least cost first search, right? It's true if N is a goal node, then A star will also always only expand the least cost path to a goal node first, but not always to an interior node. And we gave the counterexample to that right here. This where if you run A star in this, you'll expand this path first to here, even though there's a shorter path of length 3 versus 4 to this node here. Okay? A star will always find this shortest path to the goal state if the heuristics are admissible. And these are all admissible heuristics. They're just kind of goofy, right? But they're still admissible. They're positive and they're less than the true cost to go. See, this H of 10 looks big, but in fact it's less than 22, which is the true cost of the goal state. Okay, so the critical condition, we talk about it in the book. I'm not going to prove this, but you need to know it. If the monotone heuristic applies, we say a heuristic is monotone if for all arcs M and N, the heuristic on M minus the heuristic on N, absolute value of that, is less than the cost to go between those two nodes. So the difference of the heuristic is bounded above by the true cost between the nodes. Okay, so this is a general case of the special case of admissibility of a heuristic. If N here, if this N is a goal node, then this is just saying H of M is less than the cost to get from M to a goal node, okay, where H of N is equal to 0. Okay, so that's the general condition of admissibility, and that guarantees you'll always find the lowest cost path to goal first with A star. If this stronger condition applies between all pairs of nodes, then A star is guaranteed to only find the shortest path to an interior node, and it would, if these heuristics satisfy the monotone condition, it would find this path to this node before this one, and you never have to worry about when I get to a node have I got the shortest path. Because whenever you get to a node, you've always got the shortest path if the heuristic is monotone. Okay, and you can see on this example that this H is not monotone because, for example, between this node and this node, H here is 10, H here is 1. The difference between them is 9, which is greater than 2. So you can think of the heuristic difference as estimating the cost to go between two nodes. And in this case, it's wildly overestimating it, so this condition doesn't hold for this graph, which means that we get this anomaly of finding a longer path first, a longer interior path first with A star. Okay, so it's a good idea to have monotone heuristics, and I talked about when they are monotone. And for example, Euclidean distance is always monotone because of the triangle inequality, so all the ones where we used it on maps, this condition applies, we're good. If you're solving a simpler problem and using that solution as a heuristic for the more complicated problem, that's also always monotone, and so on. So, then we talked about iterative deepening depth first search, or IDS, which is depth first on a leash. We've gone through it in detail. I'm not going to go through it again. Its space complexity is linear in B and M, still exponential time. The overhead of the small depth bound is very small compared to the work at greater depths. It's optimal and complete. And then we talked about using the same idea. Instead of using the depth as the leash, use the F value as the leash, and just bump it up just enough. When you get cut off by an F value, note the node which caused with the lowest F value that exceeded the one you're using as a bound. Use that as the next bound, and just keep stepping up on F rather than on the depth. Then you get IDA star, which is not really A star at all. It's just using F values. That's the only thing it has in common with A star. It's really just iterative deepening with F values. Very pretty. Okay, so that's all just review. Any questions about the review? Okay. So another nice idea is, other than IDA star, can we use heuristic in depth first search? Yes. Say, so far we've just arbitrarily put the nodes on the frontier when we generate them in left to right order. But it's a good idea to actually use, and the order matters because depth first search is really using a last in, first out stack to expand the nodes, right? So the order matters. So you could use heuristic guidance, and two ideas are to use H, which is the guess to go, or F, which is the cost so far. And it depends whether you're trying to minimize the computational cost, in which case you'd use H, or the cost of the final path, in which case you'd use F, right? If you had a perfect heuristic, F would solve the problem without any backtracking whatsoever. Right? You just use F to guide your way down to the final solution. If H was truly estimating was equal to the actual cost to go, you'd go straight to the goal with no backtracking whatsoever. This again is very frequently used in practice. You're just really just choosing the most promising branches first. It's kind of a greedy algorithm in that sense. And you can use any kind of information available because there's really no requirement for admissibility. You could use an admissible heuristic if you want to, right? So then the question comes out, well, maybe we could combine heuristic depth first search with iterative deepening A star. What do you think? Is that possible? Any reason not to do that? Cards? Okay, so most of you aren't sure. You can't think, you don't want to commit yourself. Well, a nice idea would be just to try it. Yeah, you can try it, and it will work. Yes. You can combine it with IDA star. You could do depth first search with an F value bound using an admissible heuristic. That's IDA star, right? But when you're putting the neighbors onto a frontier, use some smart ordering of those, and that won't negate the guarantees that you're getting with IDA star, which means you could actually use a different heuristic. You're not required to use the same admissible heuristic. You can use any heuristic you want here. You could use the same one. But it doesn't have to be admissible in order not to give up the guarantee on IDA star finding the best solution. Okay? Here's another idea. Okay. Branch and bound search. So as I say, this is depth first branch and bound. There are many examples of branch and bound. The general idea for branch and bound is, suppose you've got a set of things. It might be an infinite set. And you want to find the smallest one of these things according to some criterion. Right? So what you do is you split it in half, or roughly. You just find some predicate that will divide the set into half, into two hopefully balanced halves. And you construct upper and lower bounds on those half sets for the thing you're trying to find, you're trying to minimize, right? You just keep doing that recursively. If at any point the lower bound on one set is greater than the upper bound in any other set, you can stop subdividing that set, right? Because it says that I'm bracketing the solutions for these sets, right? And this guy here has a lower bound which is greater than the upper bound in this set. So any solution in here has got to be worse than any solution in there. I can just stop cutting that one. So that's the general idea behind branch and bound. Very intuitive idea. It's kind of pretty. We're going to be much more specific, and this cutting will actually go right down to a solution and then get the bounds from there. So let's look at it in detail. So we're going to assume general arc cost positive. What you do is you just do depth first, and you find a solution, but you don't stop there. You want to find the optimal solution, right? So once you've found a solution, that's an upper bound on the cost of the best solution, right? And this, I've got a solution. It's got a cost. I'm looking for the minimum cost. no minimum solution is going to be worse than the one I got. So that's an upper bound on the best solution so far. When you can initialize that to whatever you want. It could be some very large number or some overestimate, however you get that of the optimal solution cost. And when you select a path P for expansion, you compute the lower bound on the cost of this path, right? So I've still got F, right, which is cost of the path so far plus H of P to go. This is a admissible heuristic, so that number F on the end of a path is a lower bound on the cost of any path that goes through that node, right? Any expansion of that path, right? If that lower bound is greater than the upper bound I've got so far, right? This is a lower bound on the cost of any path that goes through that node, and I've already got a path which is better than that, then I can stop. I can remove that P from the frontier without expanding it. It's called pruning the path. Otherwise, I have to expand the path, adding all the neighbors to the frontier, and it does require admissible H. Okay, so that's the basic idea. If I ever find if I get to a goal, at that point, it'll be better than the previous path I had, and that will be my new upper bound, right? So I'll keep updating the upper bound. So and it's easiest, get an idea of this by just running it on a very simple problem. We're actually going to, the simplest possible. All our costs are the same, they're 1. And H of n is equal to 0 for every n. Okay? So we're going to start here. The initial upper bound is infinity. And I've actually marked the goal nodes here. You can see there's a goal, there's a goal, there's a goal. These darker nodes are goals, right? And I want to find the cheapest goal. So one of these guys, presumably, over there. So this is the order of expanding the nodes, not of generating them, shown. I get down there. I back up. I still haven't found a goal. Bingo. I found a solution. So what's the upper bound now for the cost of a path? 5. Thank you. That's right. Because we've gone down 5 arcs, right? It's the true cost of that solution. So I keep that around, and I can now start using that to prune. So now I'm here. The cost of that is 5. I can actually prune again now. I don't want to expand that node because I can cut off, as soon as I'm equal to the upper bound, I can stop too, right? Because anything below that, I don't care if it's the same cost. I've already found a path of cost 5. I don't need to find another one. So I'll prune that one as well, right there. Okay, I'll just throw it away, like that. And then I'll back up and fail in the usual way, back up to there, and then back up to there, coming down there. And what would I do here? Prune. It's the same cost of 5, right? I've already got a solution. So then I back up, come down there, again prune there, back up to there. I've got a solution. What's its cost?
3.
Thank you. So then I've got a tighter bound, right? I'm always going to be pushing the upper bound down to lower costs. So I can prune earlier and earlier as I find paths. I get this cutoff now at level 3 here. Prune that guy. And the same thing there. Even though it's a goal, I've already got a goal at level 3, so I can prune there. And finally, I cut off all this stuff over here. So as I go across the tree, I'm going to be cutting off at higher and higher levels in the tree, throwing away more and more paths that couldn't be a solution. Okay, so it's a very simple form of branch and bound. We haven't used the heuristic costs here. If we use the heuristic costs as well, we get even more pruning, right? Because they would raise the lower bound on a path above by adding in the heuristic costs. You get the lower bound on a path is its cost so far plus the heuristic estimate. So that'll raise the lower bounds on the paths through that node, and they could be higher than the upper bound I've got already. So I'll get even and again, the tighter the heuristic bound, again, notice the higher that number we'll get, and the more cutoffs I'll get, lower bound cutoffs. Right? But I just did a simple example. You should run it in the applet. You've got branch and bound, depth first branch and bound in the applet. There are lots of examples. You can see it using the heuristic function, and notice as you get better and better heuristic estimates, you will get more cutoffs in the search. So is it complete? What do you think? See lots of yeses, some depends. Okay, so the depends have it, but it depends how you interpret it, of course. But there's the usual problem with depth first search that you might get into an infinite branch, you might get into cycles, etc., etc. But assuming you don't have cycles and infinite graphs, then yes, it is complete. And you have to, probably you should initialize with some finite upper bound as well in an infinite graph. Is it optimal? Is it always going to find the best solution? Eventually. Won't find it first, like A star, but yes, it will always find the optimal, of course. Right. It's exponential time. What's the space complexity? You just added these upper and lower bounds. They're just like two numbers, so they don't count. It's depth first search, so it's linear again, remember? Linear. Should have got that one. That's the whole point of using these depth first techniques whenever we can. Linear space, which means you've got a possibility of less than exponential time to manage that linear space. Okay, of course now you can combine BMB with other schemes. You could follow the same search path as depth first search, so you can make it heuristic depth first search. You can choose the order in which you put the neighbors on the stack. And you can use an H prime, a different H prime from the one you're using to go down. That's not admissible. But to compute the lower bound, you have to compute the F value using an admissible heuristic. To make it a true lower bound, if it's too great, it could be overestimating the lower bound and getting cutoffs when you shouldn't be getting them. And this is actually a very common technique, to use depth first, branch and bound with an admissible heuristic and another heuristic to get optimal ordering of looking at the branches. That is a very practical use of these techniques. So we've got this enormous array of possible search techniques, and now we've got some extras, branch and bound here, and not best first.
Question.
Yep.
So if you're going to use a heuristic, will we set the upper bound based on the F value of every node? When we update the upper bound, we will look at the F value?
The upper bound is only set when you actually get to a full solution, when you get to a goal. That's an upper bound, because that's the best goal, the best solution you've found so far, right?
In that case, it's equal to the actual cost, so there's no...
The actual cost of that goal, for the upper bounds. For the lower bounds, we're saying, when we get to a node, we're saying, well, there are many, many possible paths to go below this node. I want a lower bound on the cost of all of those paths. Okay, if that lower bound is greater than the upper bound of the best thing I've found so far, all of those paths are going to have a cost somewhere in here, right? So, and you're using the heuristic value to get the lower bound, right? And the higher you can get the heuristic value, the more chance you've got of getting a cutoff against the solution you've got so far. Okay? Okay, so a couple of other neat ideas. You could go backwards. If you have the search graph explicitly, it's not just generated by a generator function and it's infinite or whatever. You actually got the whole thing in memory. You could go from goal to start. There may be only one goal node and many, many start nodes. That might be a good idea to start at the goal. Or the branching factor going backwards might be much less than the branching factor going forwards. And given the complexities, we know that would be a smarter thing to do, right? Assumes an explicit goal. It's not just a goal test, so you actually have to have the goal nodes pointed to you. And if the graph is dynamically constructed, it may be impossible. So just use the forward and backward branching factors as a criterion, because it's the base of the exponent, right? This b, get that as small as possible, and you get a big win. 4 to the 100 is a lot less than 2 to the 100. Okay? Another neat idea. Well, you can go backwards. Want to go in both directions at the same time. That's a big win if you can do it, because, again, you know, if the depth from here, from start k to goal g is k, if you're only going to k over 2, then there are b to the k over 2 nodes on this side and b to the k over 2. So 2 times b to the k over 2 is much smaller than b to the k. It's like the square root of it, right? It's a much smaller number. So you can get huge wins if you can manage these two frontiers, and that might be a problem. So if, for example, you use depth first search on both sides, you can see what might happen. You might be twice as bad as just using it one direction. They might just miss, and they probably will if it's a large graph. You wouldn't be even thinking about this if it weren't a large graph. So a way of guaranteeing that you're not going to miss is to use breadth first in one direction, or least cost first search, maybe, as a secure way of making sure there's a barrier that the guy coming the other way can't get through. He's going to hit one of these nodes on the frontier coming through. Because every time you generate a node, you have to see, is it on the frontier of the other search? Okay? And so you might use breadth first or least cost first on one side, and branch and bound depth first search on the other side. Or just depth first search if you want to keep it simple. Another idea is dynamic programming, which basically builds up from the goal node, builds up a set of distances to the goal node. And we know how to do that. It's called Dijkstra's shortest path. So what you're going to build up, starting at the goal node here, is associated with each node is just the distance of that node to the goal, right? So the distance of G is 0, distance of Z is 1, distance of C is 3, and so on. Distance of B is 4, and what's the distance of K? 6, 7, infinity. Here's K. We're going to this goal node. So I see lots of yellows. That's good. So there are two paths. One that way, which is 7, and one this way, which is 6. So it's a 6. What about H? G? You can't get there from here. If you're in H, there's no arc going out of H. It has to go out. Right? So it's infinity. So initially, you initialize all nodes to infinity, and then Dijkstra will just sort of slowly decrease them, and if it finds a path to a node, it'll set it to a value. If it finds a shorter path, it'll decrease it a bit more. So this is basically dynamic programming, building up the path, sweeping backwards. And then when you run it forwards, from the start node, at each node, you can just, without any backtracking, you can trace a path through the shortest path through the graph to the goal node. Because at each node, you just look at each node coming from it, and take the one with the lowest number on it, right? Because that's the shortest distance to go from where you are. Plus, adding on, of course, the cost to getting there of that arc, right? So once you've got that stored, which you can do fairly quickly, sometimes with Dijkstra, you can then always go forward. But of course, you need to be able to store the entire graph in memory, etc., etc. A couple of other ideas quickly. Memory bounded A star. We tried to use almost no memory with IDA star and BMB. What if you got some memory? Memory's cheaper than it used to be. But you can't do regular A star because it was going to blow you away no matter how much memory you got. So you can do this memory bounded A star. Just keep doing A star and keep as much of it in memory as you can. When you run out of memory, then just throw away the highest cost path with the highest value so far from the frontier. You have to remember it in order to so you're going to trade space for time. You're going to delete it back up to a common ancestor with something with a path that already exists. And if you have to, you'll come back and recompute that later if you ever get to the point where you want to expand it again. You know, it's complete and optimal if the solution's at depth manageable in main memory. So this is now the complete set of algorithms, and I've highlighted the ones that are commonly used in practice, the ones in red. Okay, IDS, iterative deepening, because it's so simple and has other nice properties. Branch and bound with pruning and possible heuristic ordering on the nodes. IDA star, if you want full A star, this is probably the best way to implement it. And memory bounded A star at the bottom there. Okay, so these are all your learning goals. You know them, right? Memorize them and the answers, know how to do it. And know how to fill in this table. You should be able to do this cold. Right? So, moving right along. Where are we in the course? We finished search totally, but search is still everywhere. You know, it's still within, we're going to now look at constraint satisfaction and then logic and planning and so on. But all of these search algorithms we've used will still be useful in these modules, which use a more general representation of the environment. We thought of search as only working within state space representations where you've got explicit states. Right? Now we're going to say, well, for real problems, that's impossible because the state space is too ginormous. So we're going to use features instead, or we're going to use relations instead. But you still have to do search. And the search algorithm we looked at will still work. So it underlies everything. It's everywhere. So we're going to look at constraint satisfaction problems. Here, this is the focus of the next module of the course. We're going to look at two ways of solving them, deterministic algorithms and stochastic algorithms. So just recalling from lecture 2, we classified domains in the uncertainty dimension and how many actions you need to perform, and the representation scheme, explicit states versus features. And so we are going on to features. So a feature, or we'll call them variables. It's the same thing, right? A feature has a value, a variable has a value. These are algebraic type variables, so it's more useful to use that. And so you can think of an assignment to one or more variables as a way of describing a state. So you could describe a large number of states by just assigning to some of the variables, not all of the variables. And as we know, if you had 30 binary variables or features, you could represent 2 to the 30th, a very large number of states. So we're using variables, we'll use capital letters for variables, we'll talk about the domain of a variable, we can talk about Boolean, finite, infinite but discrete, and countably, not countably, but continuous, infinite discrete, or countably infinite, continuous, you know, like reals, could also be variables in this model, okay? So we, obviously, as soon as you get to these last two, you've got an infinite state space, but we can still describe it in a finite way using variables and domains. So we're going to talk about things called possible worlds, and it's important to understand what possible worlds are, and we'll also talk about models. They're a subset of the possible worlds. A possible world is any complete assignment of values to all of the variables. Okay, it's a complete description of the way the world is. Everything is nailed down. It may not be realistic. It may not be realizable. It may not correspond to a real world. That's why it's called a possible world. Okay? Some possible worlds are realizable, others aren't, because they don't satisfy various constraints and so on. So that's important to remember. We're not talking about any constraints here on the variables. All possible combinations of variable value pairs are possible.
Question?
Yeah.
Are we allowing contradictions in these possible worlds?
You can't have contradictions in the definition I've just given you, because all I've got is a set of variables. Each variable has an assignment. Okay?
So there's no relation between any of the variables?
Not at this point. No, we'll do that next. But for now, we just want to talk about possible worlds. So we'll give a whole series of examples. I'll just whip right through them. But suppose you wanted to solve crossword puzzles. The variables could be the words that are to be filled in. Right? So there's one variable. There's another variable. That's one down, that's one across, and so on. This is 3 down. The domains are the English words of the correct length, so they could fit in to those words. And the possible worlds are all ways of assigning words. I could assign one word here that started with A and another one that started here with Z, and that would still be a possible world, because there's no constraint that they have the same letter in the same place. As I say, I'm just considering assigning the variables independently at this point to get all the possible worlds. So we'll see later how many possible worlds, but what we call the dual representation is to flip that on its head and say, well, you could consider each square to be a variable, and the possible values are the letters A, B, C, D. It's 26 of them, right? The domains are the letters of the alphabet, and the possible worlds are all ways of assigning letters to cells. Okay? And that'll give us a different set of possible worlds. There may be many, many, many more possible worlds in one representation than in another one, which might be a good reason to choose the first over the second. It may not be the only reason to choose the first over the second. There may be other reasons to go the other way. But it's an important consideration, right? So how many possible worlds are there in this model where the variables are the words? Well, suppose there are 150,000 English words, but they have to be the right lengths, like 4-letter words or 6-letter words. So let's say there are 15,000 for each word. There are 63 words to be filled in this crossword. How many possible worlds are there? Assuming any combination is okay, which is what we're going to do. Okay? We've been through this before. We did this in the first couple of lectures, counting the number of possible worlds. Suppose there were one word. How many possible worlds are there? There were 15,000 ways of fitting them in. Right? Suppose there were 2, 15,000 squared. There are 63 possible worlds. So it's 15,000 to the 63. Right, most of you got that. Suppose we do the dual representation, where we flip it on its head and say the variables are the cells, domains are the letters of the alphabet. We need to know how many empty cells there are. Counting, there are 15 by 15 minus 32 black squares. 193 empty cells, 26 letters in the alphabet. How many possible worlds are there? Should be quicker than this, guys. It should just like that. In fact, the answer is right here. Domain size times the number of variables. What's the domain size? Letter of the alphabet, 26. Number of variables. Variables are the cells, individual squares. Number of variables is 193. Right? So it's green. Sudoku. The variables are the cells, the domains are the numbers between 1 and 9, possible worlds, all ways of assigning numbers to cells. We might have a scheduling problem. You might want to schedule courses in a university, jobs in a machine shop. Here the domains are pairs, right? So a course has to be given a time and a room. Okay, but I didn't say the variables couldn't have compound values. So the slot for a course would be a time room. For doing job shop scheduling, you have to specify which machine and which time a job is going to go onto that machine. So possible worlds are the time location assignments for each task, whether it's a course or a thing. Suppose you're solving the n-queens problem. You have to put n queens on a board so that none can take the other, or they can take diagonally or horizontally or vertically. We'll put them all in different columns. So we know there are n of them. We're told that. So the domains are the grid coordinates. The possible worlds are the locations of all the queens. But in real worlds, there are restrictions. In a crossword, if you have two words that overlap, where they overlap, they have to have the same letter, right? That's what makes it hard. Similarly, in Sudoku, you have all those restrictions. They all have to be permutations in various combinations. So constraints are restrictions. And we talk about three kinds of constraints. We'll talk about unary constraints that just involve a single variable. You might say this integer in this square has to be even, say. Of course, you could just restrict the domain of the variable. Instead of saying it's all the integers from 1 to 10, you could say it's all the even integers from 1 to 10, and then you don't have to add the even constraint. Or a k-ary constraint. But we're going to deal mostly with binary constraints involving two variables. But all of this works for k-ary. The algorithm just got a little more interesting, but they all go through. And there are various ways you can specify constraints. We call these either extensional or intensional. Extensional description of a set or a relation or a constraint is to list all possible values of it. So they have to be a finite number. Lists all combinations of valid domain values for the variables participating in the constraint. Right? Like if I've got two variables in integers 1, 2, 3, and I could list, constraint is greater than, then 2 is greater than 1, 3 is greater than 1, 3 is greater than 2. That would be an extensional representation. Or I could give a predicate or a function which returns true when given the values for each variable. So I don't know, I can't look at all the satisfying values. I just have to query the predicate. Say, does this pair satisfy? Does this pair satisfy? And it just says yes or no. So now we have a relation between possible worlds and a set of constraints. Okay? We said before, in a possible world, we ignore the constraints. But given a set of constraints, we're interested in the set of possible worlds that satisfy those constraints. Okay? Which is a subset of all the possible worlds. So these are the ones you could realize in the real world if these constraints exist in the world. So this is a definition, a formal definition. A possible world satisfies a set of constraints if the values for the variables involved in each constraint are consistent with that constraint. That just means for each constraint you have to check the variables that it involves, which is called its scope, and see that those values in its scope, the values of the variables in the scope of the constraint satisfy the constraint. It's a long-winded way of saying the obvious, I think. And by consistent with it means they're either elements of the list of valid domain values, which we gave up here, or the predicate or function returns true for those values. So, going back to those examples, we can add in the constraints now. We did variables and domains before. Obviously, for crosswords, since the variables are the words, the constraint is I have to check each word where it overlaps with another word and make sure they share the same letter in the corresponding position in the word. Just an equality between the two letters, right? And those are binary constraints because they're between two words, right? Two variables. However, if we do the dual representation where the variables are the cells, domains are the letters of the alphabet, we can't violate the crossing condition because we can only put one letter in each cell. We don't have to worry about that constraint. But we have to make sure that our letters in the corresponding crosswords and downwords actually are in the dictionary. Okay? Because they could be just nonsense sets of letters. So these are now k-ary constraints, and if it's, a word of length 4, it's a 4-ary constraint. It involves 4 different variables, the 4 different cells. Those 4 letters have to be in the dictionary. And the dictionary now is just an extensional representation of that constraint among those 4 letters, right? It's either in the dictionary or it isn't. Make sense?
For
Yeah.
the crossword 2, we still have the binary constraint that in a same cell it has to have or I guess that's not.
No, we don't. Because, you see, the cell is a variable.
Yeah, I see that. So.
Yeah, and it can only have one value. Yeah. So that's just taken care of by the representation. So if we go to Sudoku, then with the variables are the cells, the domains, blah, blah, we've got some pretty complicated constraints now. Each row, each column, and each row has to be a permutation of the numbers 1 to 9, and each of these 3 by 3 cells has to be a permutation of 1 by 9. So I've got 9-ary constraints. on these 9 variables, these 9 variables, these 9 variables, and all the others. So I have a heck of a lot of binary constraints involving 9 different variables saying they're all different. And similarly, in the scheduling problem, you can't have 2 classes in the same classroom at the same time. Certain tasks can't be scheduled in different locations at the same time. Like if you're in 2 classes, one student is in 2 classes, you can't have that student in 2 different classes at the same time. And so on, right? In a job shop, you often have precedence constraints. You have to do, I don't know, grinding before you do milling on a machine. So this task, the grinding task, has to come before the milling task in time. N queen's problem, that's pretty simple. No queen can attack any other queen. That's a binary relation between each of the pairs of queens in the different columns. Right? So, that's the general framework. All of those problems and millions of others. I mean, this is a huge domain of research and now of practice. There are lots of people making lots of money out of solving these kinds of problems. IBM bought iLog, which bought Cplex, which is doing constraint-based optimization, constraint satisfaction, and they use it for huge numbers of customer tasks. So this formalization is what we have to remember. So we formally define a CSP, a constraint satisfaction problem, has 3 things. It has a set of variables, a domain for each variable, and a set of constraints. Each constraint will specify its scope, which is a subset of the full set of variables. Okay? Now here's another definition. I talked about possible worlds. Possible worlds is a set of possible worlds, a set of all assignments to variables. The set of models is a subset of that. A model of a CSP is an assignment of values to all of its variables that satisfies all of its constraints. And we know what satisfies the constraints mean because we defined that. Okay, so that's the formal definition of a CSP. Given you're given a CSP, there are many things you might want to do with it. Okay? You might just want to know the yes-no question. Is there a way of solving this? I don't want to know what the answer is. Just tell me yes or no. The decision problem. Does a solution exist? Okay? By solution, we mean a model. It's something that satisfies a set of assignments that satisfy all the constraints. You might want to find one. You might want to find all of them. You might, again, you don't care what they are. You just want to know how many there are. Here, you just want to know, is it 0 or more than 0? Here, you want to know the exact number of models. Or now it gets really interesting. You might want to find the best model, take a set of all solutions, all models, and impose some criterion on them that you want to optimize. Like the one that uses the minimum number of classrooms or the minimum time in the job shop or whatever. That's what we call a constraint-based optimization problem. And more higher level, you might say, is it true that in all solutions that, all classrooms are used all the time, say. Some query about all the solutions without wanting to know what they are. I just want to know some property of them. All of those are possible ways of thinking about it. But they're all technically hard. They're all NP hard. And even with finite domains, even the simplest problem, determining whether or not a solution exists, is hard. So there's no known algorithm with worst-case polynomial runtime. So you can't hope to find an algorithm to make it efficient. By efficient, we mean low-order polynomial. Or even higher-order polynomial, but... So we have to do various approximations, and that's where we'll end it today, but we'll then talk about approximations, good ways to approximate solutions, or what happens in the real world.